Professor of Mathematics at the Mathematical Institute at the University of Oxford in England. His work on black holes and quantum gravity had established him as a world leader in mathematical and theoretical physics. In addition to the recent honor of knighthood, Professor Penrose earlier was awarded the prestigious Wolf Prize for Physics. It was in 1988, which he shared with Stephen Hawking. In addition to a large list of technical publications in mathematical physics, Professor Penrose has published advanced research monographs on techniques of differential topology in relativity and spinors and space-time. A more popular treatment of related topics appeared in 1996 in a book entitled The Nature of Space and Time, which was with Stephen Hawking, or was like Penrose and Hawking, Penrose's view and Hawking's view, which are not entirely the same. A great little book called The Nature of Space and Time, which is reasonably accessible. But Sir Roger Penrose is perhaps more well known to a wider audience for his work in the field of tessellation, or tiling. The imagery of what is now referred to as Penrose tiling has entered the modern intellectual lexicon. Indeed, Penrose tiling is now the subject of a lawsuit in the United Kingdom, where there's an apparent copyright infringement, emphasize apparent copyright infringement, due to the use of Penrose tiling as a decorative pattern on a particular brand of toilet paper. This is real, it's fun. We were out at University of Portland today for a luncheon with Dr. Penrose too, and it's interesting that several people are looking to put Penrose tiling in their, this aperiodic Penrose tiling. It's not normal tiling, it's much more interesting, in their kitchens and things like that, and it's doable, but not many people have picked up on it yet. I'm going to look into it soon. A wall of Penrose tiling. Anyway, and those of you who don't know this, you have to look it up. Related to this work, interesting point, related to this work in the field of tessellation, Professor Penrose and his fathers are actually the creators of the famous Penrose staircase and the impossible triangle known as the tribar. Both of these impossible figures were used in the work of Dutch graphic artist Marie Moratz, get his first name, Escher, anyway, to create structures such as a waterfall where the water appears to flow uphill, and a building with an impossible staircase which rises or falls endlessly yet returns to the same level. I'm sure you've all seen that. Started with Roger Penrose. In the last few years, this fertile intellect began exploring the science of mind. This has resulted so far in two very popular, influential books. One several years ago, I believe 84, entitled The Emperor's New Mind, and then a follow-up to that responded to critics and commenters on The Emperor's New Mind called Shadows of the Mind. I have Shadows of the Mind for sale out there. I didn't get Emperor's New Mind, sorry. His most recent thoughts on the science of the mind, however, are contained in his latest book, just out this year, for which we took the title of tonight's lecture as well. It's called The Large, the Small, and the Human Mind. Clearly, Sir Roger Penrose is one of the great intellects of the latter part of the 20th century. Ladies and gentlemen, please join me in extending a warm Oregon welcome to Sir Roger Penrose.
Well, did I plug myself in correctly? Good, thank you. Well, thank you very much, Terry, for those remarks. As you just heard, the title of this lecture is The Large, the Small, and the Human Mind. So let me begin by trying to give you some feeling for what the large and the small, how large and how small the large and the small are. So what I have here is the scales of distance, it's distance on this side, and the scales of time on this side. So the shortest time that one ever considers in physics is something called the Planck time. It's really much too short. It's not something that any known physical process takes. It doesn't take that time. The shortest known physical processes are the decay times of the very shortest lived particles, and they're about 20 orders of magnitude longer than the Planck time. When I say an order of magnitude, that means 10 times. Now that's just about here. Right up at the other end of the scale, we have the total age of the universe, something up to now, which is something like 10 to the power, well, not quite 10 to the power 20 seconds. And that's a big scale. Now, on the other side, I have the distances where you go from one side to the other by the speed of light. So, where we have second over here, we have on the other side a light second. Sometimes people talk about distances in terms of, well, light years and so on. So here's the year, and so a light year would be on this over here. And the age of the universe, the age of the universe is over here. The radius of the visible universe is somewhere up here. And you see this enormous scale. And right at the bottom we have a thing called the Planck Length. Now the Planck Length and the Planck Time are sort of theoretical notions. Sometimes the Planck Time is called a chronon. It's the sort of, if you like, the shortest time that one might consider in physics. It's the kind of time which comes up when you try to combine Einstein's general theory of relativity with quantum mechanics, but it's not something which features in processes that we directly know. The smallest kind of size that we experience are the sorts of things like the sizes of fundamental particles and so on, and that's round about here. Notice that the human size is somewhere in the middle of this scale. Here's the size of the Earth and so on, the size of a cell. Human size is somewhere in the middle. Now one thing I'd like to point out is if you take lifetimes, a human lifetime is way up here, which is pretty well getting on for the age of the universe. So you might think that sort of human existence, and sometimes people complain that it's kind of ephemeral. Well, I'd like to point out that we live almost as long as the universe. Of course, there's a fair range from here to here, but the point I want to make is that there are far more sort of timescales of particles in a human lifetime than there are human lifetimes in the age of the universe. So, from that point of view, we do live an awful long time. Okay, well, let me set this on the other projector, if I can remember how to turn it on. And here we are. I don't know if, yeah, we can get it all on. There we are. Just so you can stare at that. Now, one thing that's perhaps I want to stress, and why that we talk about the large and the small, sort of separately, is that the kind of physics that's used to describe large-scale phenomena, sort of up this end of the scale, tends to be different from the kind of physics that we use to describe small-scale phenomena. You use quantum physics down here, and you use sort of classical physics up there. And they don't really fit very well together. And one of the things I want to stress is this fact that we do use two types of physics which don't really fit all that well together. And the third part of the title is the human mind, and the argument is that in order to understand mentality, we're going to have to know something about how these two different schemes fit together, and somewhere in the boundary, the borderline between these two realms of physics, is a new realm of physics that we're going to have to know in order to understand mentality. So that's the sort of thing I want to talk about. And in order to put, perhaps, the whole talk in perspective, let me give you this picture here. It's something which is actually taken from Shadows of the Mind. It's the picture, not in colour, in black and white I should say, occurs in the final chapter of Shadows of the Mind. That chapter is entitled 3 Worlds and 3 Mysteries. The worlds are, well, let's bring this up here. The worlds are, on the one hand, the physical world, which is talking about the things I have been saying over there, physical objects like this table and so on, physical things. That's indicated by this blue sphere here. There's the mental world, that's the world of our perceptions, our feelings, our consciousness, and I've drawn this out here. And one of the mysteries, the various mysteries are indicated by these arrows. One of the mysteries, and I'll be primarily concerned with that, is how it is that mental qualities can arise in connection or somehow out of, I don't know if that's the right way of saying it, but physical objects. Living human brains, at least, seem to evoke mentality, and that is the green mystery here. I've got the bottom part of the picture. But in order to understand these things, and I want to concentrate a little on this in my talk, we have to consider what I regard as another world, that is the Platonic world of mathematical truths, or if you like, Platonic world of absolutes. Now, the Platonic world plays roles both in the structure of the physical world and in relation, in what I want to say, to our mentality. You see, there's this mystery here, which is stressed particularly by the physicist Eugene Wigner when he wrote an article entitled The Unreasonable Effectiveness of Mathematics in the Physical Science. You see, he regards as quite extraordinary that physical objects behave according to mathematical laws, to a tremendous precision. It's not just the precision, but the kind of mathematics that you need in order to describe the way physical objects behave is really a very subtle, sophisticated kind of mathematics. And there is a deep unity between mathematics and the way that the physical world operates. And it reflects the mathematics one sees in the operation of the physical world also reflects back in our understanding of mathematics. So the arrows really go both ways in a sense. But I've had it in this diagram almost as though the physical world seems to emerge out of this world of Platonic mathematical absolutes. Some people have trouble in believing in the existence of this world at all. If you're a mathematician, it's very natural because you tend to think of mathematics as rather like archaeology. You're sort of digging away and trying to find what's out there, what the truth is that's somehow outside us and beyond us, and something which is not personal, not individual, it's something transpersonal or pan-personal. This world which seems to have an existence of its own. I think if you have trouble believing that it has an existence of its own, the way I would argue that it's really hard to argue any other way, that is to say, if this world were merely the product of our mentality, then it's hard to see how the universe, which has been around a long time, a lot longer time than we have, how is it that all that time when we weren't around, it was operating according to very precise mathematical laws. And these laws are very precise. It's not something we impose on physics, it's something which is out there in the way the world operates. So somehow, this part of the diagram was there long before there were any human beings. So it seems to have some kind of existence independent of ourselves. Well, however you look at it, it's not necessarily vital to what I want to say, but I do want to say something about this mystery, which is how is it we actually are able to perceive mathematical truth. Is it the result of our performing some kind of computations in our head, or is it something else? And that's an important aspect of what I want to say. So perhaps I'll put this over on the other side, and just so you can keep that in mind. And I want to say something about the mental world. In particular, I want to say something about the phenomenon of consciousness. And the question is, can we hope to understand it in terms of, well, I mentioned possibly computation. Is it just a matter of our doing some elaborate computations in our head, and whatever they are, somehow, if we do the right ones, that consciousness comes about? That's a view which has been expressed by quite a lot of people these days, but maybe that's not right. If it's not right, then can we explain consciousness in terms of existing science? Is our scientific worldview adequate to accommodate the phenomenon of consciousness? Or perhaps not. Perhaps we're going to need something outside existing science in order to understand consciousness. Perhaps it will require some kind of extended physical worldview. Or you might say, well, perhaps it's wrong to think of consciousness at all in terms of science. Perhaps it's something outside science altogether. Well, I'm going to try and argue that it's number 3 that we need, that is to say, consciousness is something that ultimately we should be able to understand in some kind of scientific terms, but these scientific terms will be not within the scope of the science that we know now. It will require something beyond the science we know now. And in fact, I'm going to try and argue, well, that it's to be found in this sort of borderline between the large and the small. So that's really what I want to try and argue for. We don't know the physics yet, but it's something that I hope we will be able to come to before too long. And there will be arguments from philosophy, mathematics, physics, biology, psychology. Well, I'm going to concentrate primarily on certain arguments from mathematics, and then I'll move on to physics, and then at the end I want to make a few remarks about biology. So that's more or less the plan of things. Now, consciousness has many manifestations. There are sort of two aspects, if you like, two polarities of consciousness. You could talk about consciousness in its passive role, and that's the sort of thing that philosophers call qualia, one's feelings, perceptions. If you look at something red, then you have this perception of a red thing, and that's an example of a qualium, or the feeling of pain, or something like that. On the other hand, there's the active aspects of consciousness, and usually the term free will is used to describe how one uses consciousness in an active way. And I've listed a number of terms here. Now, I'm not really going to talk about most of those things. I really have no idea how redness somehow comes about. What is it that things of that nature? What is pain? I'm not going to try and address those issues. They're not anything which I really have anything significant to say about. However, I do want to concentrate on another term, which is the word understanding. Now, understanding seems to be somewhere between the passive and the active, somewhere perhaps in between there. And I think one can begin to say something about understanding. And the question I want to raise is whether a computer or a computer-controlled robot would be capable of genuine understanding. And understanding seems to me to have importance. Well, I put 3 words down here: intelligence, understanding, and awareness. Now, there are 3 words that I would hate to define. I don't really know what any of them mean. However, you might say, why am I talking about them if I don't know what they mean? Well, being a mathematician, I can get away with that kind of thing. The main thing is that it seems to me there are clear implications between these words. That's just to say, I think it would be unreasonable to say of an object that it possesses intelligence if it possesses no understanding. It seems to me understanding is a prerequisite for intelligence. In other words, intelligence requires understanding. Likewise, I think it's unreasonable to say that an entity could possess understanding if it has no awareness. It seems to me that you have to be aware of something to understand it. So I would say awareness is a prerequisite for understanding. In other words, understanding requires awareness. So therefore, if understanding can be shown to be beyond computation, and that's what I want to try and demonstrate, that understanding is something outside the scope of what can be done by a purely computational action. If understanding can be shown to be beyond computation, then intelligence is not a matter of computation either, and moreover certain aspects of awareness are therefore also beyond computation. It might be that all aspects of awareness are not computationally attainable. In fact, that would be my opinion, that awareness is something quite different from what you can achieve purely computationally. But the arguments that I will give are only to do with understanding and not other aspects of awareness. Okay. Well, we know one instance of something where computation has been extremely effective at doing things that one might have thought required intelligence, namely playing the game of chess. We know that computers, at least some computers, some computer programs, can play chess extremely effectively, to the extent that in a recent match with the world chess champion Garry Kasparov, the computer was able to win. Now, I want to raise the question that even though computers seem to be able to play chess extremely well, do they understand the game? Does a computer understand what it's doing? I think a good case can be made that even in such an activity as chess, where computers can be so effective, that they actually possess no understanding whatsoever. And I want to show you an example of a chess position. This is given in the Shadows of the Mind. It's also given in the Large, the Small, and the Human Mind. It's a chess position, I believe, due to William Hartston. And the idea is that white, or brown if you like, has to play and draw. Well, you see, you don't have to know much about chess to appreciate this position. The black pieces, you see, there are 2 extra rooks and an extra bishop, which should be an absolutely overwhelming advantage for the black pieces. However, you'll see that there's this barrier of pawns which goes right across from one side to the other, and so in order to draw the game, all white or brown has to do is to wander around at the back here, make sure the barrier of pawns is left intact, and there is no way that black, no matter how well black plays, there's no way that black can win the game. However, if you show this position to virtually any chess computer, and it was shown to, in particular, the computer Deep Thought, which was the best chess-playing computer of its day, the sort of predecessor of Deep Blue, and what did it do? It took the rook with its pawn, opened up the barrier of pawns to achieve a hopelessly lost position. You might say, why does it do such a stupid thing? Well, you can actually understand why it does such a stupid thing, because, after all, it's programmed to make move after move after move after move after move, down to a certain depth, and then it has to make some kind of assessment as to whether the position is improved or not, and one of the criteria would presumably be counting up the number of pieces and so on. And if it can only compute so far down that it hasn't actually got checkmated yet, you see, it takes a long time for the pieces to pour through the hole and eventually checkmate the brown king. So if it can't quite get that far, it won't realize that the position is actually much worse when it's taken the rook. Well, you see, I said this was given to Deep Thought. It was actually also given to Deep Blue. So what did Deep Blue do? Well, it took the rook with the pawn. So I'm just giving this an example. Of course, in most positions, Deep Blue would make wonderful moves. But the point is that this thing rather picks out the distinction between what you can do by brute force computation and what you can do by understanding. In fact, this position was one of a number of positions that were made up by William Hartston and David Norwood. It was an example of what's called a Turing test. A Turing test is something where you have a number of computers, perhaps a number of human beings, and you have to try and tell which are which simply by what they do, maybe in a computer terminal or something like that. And these positions, there were a number of chess positions, half of which were easy for humans and hard for computers, like the one I've just shown you, and the other half were easy for computers and hard for human beings. And these positions were given to the human beings and computers, and they had some reasonable sort of time limit, and it was an almost completely clean test. You could tell exactly which were the humans and which were the computers. So whatever it tells you is that human beings and computers certainly do different, they play chess in completely different ways. Here is another position which was one of those. You see this position that I just showed you before. You might, of course, somehow program into the computer, well, if you see a barrier of pawns like that, well, then make sure if you're losing you don't let it get damaged. Well, then if you gave it this position, it might still not know what to do because the barrier of pawns is not complete. And if you give that to any chess-playing computer, which is not specifically programmed to take care of this specific position, what will it do? It will take the rook with the bishop, and that's the wrong thing to do. What you're supposed to do is put the bishop here and make a new barrier where it's not quite a barrier of pawns because there's a bishop sitting there and pretending to be a pawn. But it's essentially the same position. Okay, well, that's just an example to show you that there is this distinction between understanding and brute force computation. Of course, to some degree, brute force computation can offset understanding. And you can sort of play one against the other. You see this in everyday life too, or in science, that sometimes you find people who are very good at computation and don't have much understanding, and they can get away with it. But with a certain amount of understanding, you can circumvent a lot of brute force computation. But the trouble with chess is that it is a finite game, and so ultimately you could imagine having a computer so powerful that even without any understanding, it could make the right moves in positions like this. So it would just compute and move after move after move after move so far down that it in fact could resolve positions of this nature. Or you could put various other things into the way the computer operates. And so in a certain way you can't really completely distinguish between understanding and brute force computation using chess. The difficulty being that chess is a finite game and there are just a limited number of possibilities and a limited number of things you could do. So in order to make this distinction clearer between understanding and brute force computation, you really have to turn to something which is potentially infinite. And this means, in effect, one has to turn to mathematics. So let me move on to mathematics. I don't have to talk about particularly sophisticated mathematics. I'm going to talk about the mathematics of ordinary natural numbers. Well, my natural numbers start at 0. Sometimes people start with 1, but that's not an important point. The natural numbers, these are the non-negative whole numbers. 0, 1, 2, 3, 4, etc. Now, how would you prove a statement which is supposed to hold for all natural numbers? Some statement which is true for all natural numbers. How would you establish such a thing? Well, there's a well-known procedure in mathematics known as mathematical induction. I hope people still learn this over here. I get worried about whether we still learn it in England. The idea is that if you want to prove something P of n, where n is a natural number, and you want to prove that that's true for all natural numbers n, you have to establish two things. One of them is that it's true for the first one, 0. So you establish P of 0, and that's just maybe some simple thing to do. And then you have to show that if it's true for n, then it's true for n plus 1. And each of these may be some finite calculation of some sort. And if you've established both these things, then that tells you that the thing P is true for all n. And that's what's known as the principle of mathematical induction. It's a very powerful thing. It enables you to prove all sorts of things are true for all n by means of some finite process. Well, that's sometimes referred to as the rules of piano, first-order piano arithmetic. Don't worry too much about that. If you're a logician, you might want to know what I'm talking about, and that's what it is. Now, I want to raise the question here, are computational rules, such as those given by mathematical induction, are they sufficient for proving ordinary statements of arithmetic, such as, for example, the famous Fermat's last theorem that was proved by Andrew Wiles recently? That's a statement for all n something or other, that kind of statement. Well, what Geillis theorem, this famous theorem due to Kurt Gödel, tells us is that no. Let me just read this a little bit clearly. You see, are computational rules such as those provided by ordinary mathematical induction sufficient for establishing the truths of arithmetic? Well, Geillis theorem actually tells you that this can't be true. If you look at it carefully, it tells you something a little more than that. It tells you that the truths, mathematical truths about natural numbers that are perceivably true, in some sense, how we perceive mathematical truth are not constrained. The way in which we perceive mathematical truth is not constrained by any system of mathematical rules. But I want to let me put this up on the other side so you can stare at that. But I want to, rather than giving you a proof of the, let's put mathematical induction there, I guess. We get that on. Rather than giving you a proof of the Gödel theorem, which is actually not that hard to do, and it's something which I could do here, I want to give you an example which illustrates it. Sometimes people say, well, okay, this may be true, but it's not really important for mathematical things that we're interested in. I want to give you an example of something. I only read about this fairly recently. It's not in any of the books that have been mentioned here, but I thought it's worth giving it to you here. It's a theorem due to Goodstein, proved in 1944, and it's a nice example because it's something you can explain to people who don't know a great deal of mathematics. They just have to know a bit of basic mathematical notation. Now let me just describe this. It has to do with natural numbers generally, but I want to illustrate it by taking a particular natural number. I'm going to take the natural number 1077. But what I want to say applies to natural numbers generally. We'll try it with 1077. Now the first thing you do is write it in a binary form. So you have noughts and ones and so on. Well, these noughts and ones stand for powers of 2. So the one at the end stands for 2 to the 0, that's 1. This one is 2 to the 2. Any number can be expressed in terms of a sum of distinct powers of 2, and those powers of 2 which are present in the sum are represented by 1s, and those which are absent are represented by 0s. So 2 to the 10 is 1024, 2 to the 5th is 32, etc. 2 to the 10, of course, means 2 times 2 times 2, 10 times. And so here I've written 1077 in terms of powers of 2. That's basically what the binary scale does. But then you might look at this expression and say, well, I've got the number 10 written up there, and the 5 and the 4. I haven't written them in powers of 2. So let's write 10 as a power of 2, and likewise with the 5, and so on. 10 is, after all, 8 plus 2. That's 2 cubed plus 2. So I've written the 10 as 2 cubed plus 2. The 5 is 2 squared plus 1, and 4 is 2 squared. So I've written all the exponents now also as powers of 2. But then you say, well, I haven't really finished, because what about that 3 up there? I've written that as a power of 2. All right, well, I'll write that as a power of 2 as well. So we have 2 to the 2 plus 1 plus 2 plus 2 to the 2, etc., etc. And any number can be written in terms of powers of 2. You may have to go up higher here, but any number can be written in this kind of way, simply in terms of powers of 2. Okay, now I want to describe what Goodstein's theorem tells you. I want to describe two operations. The first operation is to look at the 2's in this expression. I'm going to call that the base. And the base is to be replaced by one more. So the 2 goes up to 3. And now that expression has become 3 to the 3 to the 3 plus 1 plus 3, etc., etc. It's of course got much, much larger. It's much huger than it was before. Okay, well that's what I've just done. The second operation, that one was A. The second operation is B. That is subtract 1. So you take the 1 off the end here. It hasn't made much difference. But there it is. 3 to the 3 to the 3 plus 1, etc., etc. And then I just do that again and again and again. I do A again. That's replacing 3 by 4. The number has gone shooting up much, much bigger. And then I subtract 1. Well, it's not quite so easy as before, because before I had a little 1 handily sitting at the end there. Now it's a bit like taking 1 away from 1,000, you get 999. Of course, you know you can do that. Here, I'm using base 4, so rather than 9s, I get 3's. So it's 3 times 4 cubed plus 3 times 4 squared, etc., etc., etc. Well, that's all right. I can subtract 1 and still write using this 4. Then I replace all the 4's by 5's. Of course, the 3 now can stay put, because that's smaller than 4, and so it's smaller than 5 too, and that's just a coefficient, you don't count that. But the 4's go up, they become 5's, and the number has got much, much larger. Okay, well, I'm just going to do that, A, B, A, B, A, B, like that, and just see what happens. But what happens here? We started with 1077, then it goes up to something, the green ones will be something of the general order of 10 to the power 40, the purple one, something like 10 to the 600, the brown ones something like 10,000, and they'll just go shooting up and up into the stratosphere and way out into the farthest reaches of the universe, and they get larger and larger and larger. What does Goodstein's theorem tell you, though? They tell you that if you keep going, you end up with 0. That is to say, this little operation of subtracting 1 finally wins. It's quite amazing that the operation A, which is making the number get bigger and bigger and bigger, is finally, this little operation finally wins. It's wonderful. Well, I want to tell you a few things about this. First of all, it's true. Secondly, it can't be proved by mathematical induction. So if that was all you knew about natural numbers, you couldn't know this. However, it's not that hard to prove. You just can't do it that way. And this is a result due to Paris and Kirby. They proved this in 1982. And I want to give you an argument. Well, it's the sort of thing that if there are mathematicians in the audience who know the right kind of mathematics, they have to know about transfinite induction, then the proof is almost immediate. I'll give you the idea of how it works, and then I'll just try and describe why it works in a minute. If you know about transfinite induction, you say, oh yes, my heavens, it works. Well, anyway, here's the proof. You just imagine this written down, this calculation, written down on an enormous sheet of paper. It could be absolutely vast, never mind. It could be infinite for all you know. Written down on an enormous piece of paper. And what I'm going to do first is block off the base by a black splodge. And now operation A simply doesn't do anything, because you don't see anything underneath the splodge, just the same as it was before. But B, of course, does. Now, if you know about transfinite induction, what I'm telling you is that that black splodge stands for Cantor's first first infinite ordinal number, which is called omega. These things then become what Cantor calls ordinal numbers, and you have a descending chain of ordinal numbers, and such a descending chain always has a first member, and that first member has to be 0. And that's the proof. But of course, if you don't know about ordinal numbers, that may not help too much. But let me give you the gist of the idea. See, basically, what one has are these kind of towers of exponents. And each time you chip away, and the one at the end sort of falls down and produces a whole string of other things. You chip away at them, chip away, chip away, chip away, and then the next one falls. And it goes on like that until finally you get to the tallest one at the end here, and then that falls. It takes an awful long time, but when that happens, you just eat them all away, and then the subtracting one operation just chips everything away and kills them all off. I would recommend, it's a nice little exercise when you go home tonight, try it with 4. You'd be surprised how high it has to get. 3, you could try 3 first. 3 is actually quite easy, but 4, you really get the idea if you try it with 4. Okay, that's just something I would suggest. Now that's an example. The fact that you can't prove this using mathematical induction is an example of a Gödel theorem. So this is what I've just shown you, is a Gödel theorem. It's a Gödel theorem for the principle of mathematical induction. Gödel theorem is actually rather more general than that, and very much more general than that. It tells you that whatever rules you had, not even just only mathematical induction, whatever rules that you chose, there would be something like a Goodstein theorem which will defeat those rules, but yet by using insight you'll be able to see it still is true. In fact, the way that Paris and Kirby prove that this lies outside mathematical induction is to show that you can construct funny kinds of numbers, the sort of thing that Hofstadter calls supernatural numbers, where it really means non-standard numbers is the technical term. You construct these funny kinds of numbers which satisfy the principle of mathematical induction, but for which the Goodstein's theorem is false. And that shows that this thing can't follow from that. So that's the sort of way it works. Another way of thinking about these things then, or another way of thinking about Geillis theorem, is it tells you that no system of computational rules can characterize the properties of the natural numbers. You don't know that you haven't really been talking about these supernatural numbers instead. You see, there are always these non-standard models, as they're called. So I say what Hofstadter calls supernatural numbers. Now the point I want to make is that it's very easy to tell these funny kinds of numbers from the natural numbers. Nobody would be fooled by that for a minute. You can tell a child what the natural numbers are. Any child who's learnt, the basics of arithmetic knows what the natural numbers are. And you don't give a child computational rules. You don't say learn induction. You don't say child. You say, okay, you give them a few number of apples, a number of oranges and bananas and things like that. Sort of thing they do in Sesame Street. And then they get the idea, 3, 4, 2. It's best not to start at the beginning. It's a bit hard to get the idea of 1 until you've got some of these bigger ones. But, okay. The question is, what on earth is a child doing when a child perceives the notion of a natural number? It's not being taught rules. It's gaining some kind of understanding. And this is an example of what I would consider to be what I have in my diagram here, of this orange arrow here. It's somehow making, I put it like this, although I get into trouble often when I talk about the atomic world, it's somehow making contact with this notion, these Platonic notions. That's, in a way, what the child is doing. And in order to make this contact, awareness is essential. So what I'm trying to argue is that in understanding what natural numbers are, the child is necessarily employing its awareness. It's something that merely having computational rules, it would not be capable of doing. And that a computer, I would argue, is therefore not capable of making this contact and is not capable of having the kind of understanding that enables us to see that Goodstein's theorem is true, for example. I can give you another example, because I think it's fun, as mathematics should be. It's in the same paper of Kobe and Paris, 1982. It's another thing, very much like Goodstein's theorem, but it's a bit more general. It's called Hercules and the Hydra, and here I've got my artist's rendering of Hercules and the Hydra. I don't know what Hercules really looked like, but that's the best I can do. I don't know what the Hydra looked like either, but I've sort of guessed it looked something like that. Now you see, Hercules is trying to kill the Hydra by chopping its heads off. It's got loads of heads. And the problem is that when it chops a head off, the Hydra grows some more heads. And so Hercules keeps chopping away and it keeps growing new heads. Well, in the actual story, Hercules cheated, but I'm going to have an honest story here. Now, but you see, mathematicians don't quite like all these complications. They like to simplify things, and so I've drawn the essentials here of what the Hydra is. It's what your mathematician would call a tree. And the rule is that if we see Hercules is about to chop that one off, which is in my diagram this one here, if that gets chopped off, the rule is, okay, remove all that, and then you go down one to this point, and then you see what's above that, and then you grow a whole new one, like that. So whereas there were 3 heads on the ends there are now 4 heads on the end there. So Hercules has lost a bit in that there's another head. Next time, Hercules chooses to chop that one off, and you then go down to here, you see what's above that, and now, this is the catch. It doesn't just grow 1 more, it grows 2 more of that. So Hercules panics a bit at this stage and decides to chop that one down there. It's actually a mistake, but let's say he chops that off. He thinks he's done all right because that just comes off and there's nothing below, so it does come off. But you see all the time the Hydra has been going, the 2 has gone up to a 3 now, so next time it's going to go 3 of whatever it was, or the next time after this 4 of them. So when Hercules chops that off, it actually grows 4 new things. And then Hercules decides to chop that off and it grows 5 and so on. And it goes on and on like that. Well, the theorem is that Kobe and Paris argue, very much like the Goodstein theorem, that no matter how stupid Hercules is, he always wins. So eventually, the Hydra gets chopped and gets killed. And it's rather remarkable. It's the Goodstein theorem is an example you can, it's a particular case of this. It's where a particular sort of chopping operation takes place. But even though Hercules made a mistake, I said this was a mistake, it just means it's going to take much, much longer, that's all. But he does finally win. And the way you prove it, I'm not going to go into this here, but it's again ordinals, and you construct ordinals out of trees and so on. And the particular tree that I had with 1077 is that one. let me not go into the details. It's just another example of something which evades the rules of mathematical induction. Something where you need new insights, and not those which are given by simply those rules which you might have learnt. Now, let me say a little more generally what Geillis Theorem says. It has to do with the perception of mathematical truth, or at least the particular aspect of it that I am making use of here. And what I'm arguing is that the perception of mathematical truth cannot be reduced to a set of mechanical rules. In other words, computational rules. More specifically, Geillis Theorem tells us that for any set of mechanical theorem-proving rules R, we can construct a mathematical statement G of R, which has the property that if we believe that these theorem-proving rules don't give us wrong answers, if we believe that they are sound rules, they actually can be trusted, if we believe in them, then we must accept as true something else, that is G of R, and moreover G of R cannot be proved using the rules of R alone. So what that's telling us, that for any set of rules we actually are prepared to use and believe in, we can see how to transcend. That's what Geillis Theorem definitely does say. So although often people argue about the use of Geillis Theorem in the context in which I'm using it, this you can't argue with, that's certainly true. Perhaps I could make it a little more precise here, what the Gödel, it's a slight sort of Turing's version of the Gödel theorem, if you like. What it tells you is that mathematical understanding cannot be encapsulated in any system of knowably correct computational rules. So the rules which you know and believe in, any such system of rules can't encapsulate our mathematical understanding. And you can restrict attention to clear-cut arithmetical statements like Fermat's last theorem, which I say was recently proved by Andrew Wiles. Or if you like, I can make the statement a little closer to what Gödel said. Given any such system of computational rules, Gödel shows how to exhibit an arithmetical statement whose truth is seen to follow from the correctness of the rules, yet it does not follow by application of the rules. So if you're prepared to use the rules, you believe they're right. The way that Gödel says is that if you believe they're consistent, if you're prepared to use them, you have to believe they're consistent. Then you also must be prepared to transcend them. Now, that's certainly correct. There's no arguing about that, although I may say people try to argue about that, but that's correct. If they argue about it, they're wrong, I should say. But there is a case that can be made, of course, and that is that we may use computational rules of some sort, but they may not be correct, they may be approximate to something, and they may not be knowably correct. We may not know that they're right, even if they are right. And so this raises issues which are quite subtle issues that have to be addressed. And I do try to address these in some detail in Shadows of the Mind, and if you're interested, I would recommend looking at those arguments. I'd also recommend making sure you understand them, because I think some people have missed some of the main arguments that are in there. In fact, most people seem to have, unfortunately. Must have done something wrong somewhere. But anyway, you can raise the question, you see. Perhaps mathematicians unconsciously use some system of rules they cannot know to be correct. But then you can raise the question, how could these rules have come about? Well, I'm not going to go into the arguments here. I really refer you to Shadows of the Mind, and perhaps to the psychic discussion, which is in the World Wide Web. But rather than doing that, I just want to give you a cartoon here, which is from Shadows of the Mind, and the large, the small, and the human mind. The argument is that it's very hard to see that if we are using some very sophisticated rule way beyond mathematical induction, that's not enough, if you see, it's not enough for Goodstein's theorem. But if we are using some very sophisticated rule inbuilt into our heads, how do they come about? Well, presumably the scientific argument would be that they come about through natural selection. But it seems to me that there's very hard to see how that could be, because natural selection certainly does not seem to favour mathematicians. I'm not sure on the whole they're terribly well paid, but that's not so important. It's what happened in the remote past, And here I have a mathematician working away at his figures on the ground here, and he's not likely to have any more children because he's about to be eaten by a saber-toothed tiger that he's not looking at. His mathematics isn't helping him much in the kind of world that he's grown up in. However, his cousins, one over here who's designed some wonderful new mammoth trap, some other cousins who have built shelters, have learnt to domesticate animals, and have learnt how to grow crops and things like that. No doubt the kinds of things that we did get selected for. What I'm trying to argue is that all these things are manifestations of the general quality of understanding, and that quality of understanding potentially is something which enables us to see our way through things like mathematical induction, things like Geillis Theorem, which transcend any set of mathematical rules. So, understanding, I'm trying to argue, is not some very complicated set of rules. It's something which, in essence, is perhaps simple, but it's not computational. If it's computational, then one falls into the Gödel trap, and perhaps I'll put the Gödel one up here rather than an induction. I'll put this version on, it's perhaps the easiest to understand. So I'm trying to argue that in our understanding, we're using something which is outside computation. The computation does not encompass understanding. Understanding is something different. In fact, it's the sort of thing that if you use computers, you certainly sort of feel this because you use your understanding in order to understand whether what the computer tells you at the end, what it means. You have to use your understanding to know what kind of program to put on the computer. The computer does the computing, that's fine. But the understanding of what that computation is all about is something you have to do. So understanding, I argue, is something which is not encompassed by computation. However, I'm certainly not saying that it's outside the operation of the physical world. So what I'm trying to say is that out there in the physical world, in the way the world operates, is something of a non-computational nature, and that we have made use of that. Natural selection has taken advantage of that and has developed it to a high degree in human beings. It's also present, I would argue, in other animals, but to a high degree it's been developed in human beings, and that's what we make use of. That's how we had an advantage over other animals, because we evidently had more of this quality than they did. And it's also the quality that we incidentally use in mathematical arguments. So that's my claim. Now you might say, that's all very well, but how on earth could you have something which is scientifically understandable or scientifically describable which is outside computation? I think people find this particularly hard to grasp nowadays because science is so often dependent upon the use of computers. One tends to say that a scientific theory is only a good theory if you could see how to put it on a computer to see if it works. And what I'm trying to say is that you could have a perfectly respectable scientific theory which is beyond computation, which is not computational. And to illustrate this, I want to show you a toy model universe. It's the kind of thing that physicists do when they can't think of anything better to do, to construct toy models of the universe. When I say toy model, I mean that it's not something which is even intended to mirror the way that the actual universe behaves. It's simply meant to illustrate a point. And that's all I'm doing here. So don't try to think this is anything. I don't think the universe is like the model I'm going to show you, but the model I'm going to show you is something which has this property of non-computationalness. Well, it's really a stupid little universe, but it has a kind of time which is discrete, just goes 0, 1, 2, 3, 4, like that. And the state of the universe at any one time is given by a pair of polyomino sets. Well, I have to tell you what polyominoes are and what a polyomino set is. So let me use this other machine to give you some examples. There are two examples of polyominoes. They are simply plane shapes made up out of squares glued together along their edges, the squares all being the same size. And the question that I want to raise, if you're given a set of these things, is whether or not you can cover the entire plane with the given set of polyominoes without any gaps and without any overlaps. So if you take this cross, for example, yes, you can do it, and you see I've started to do it here, and you can imagine that that pattern will continue indefinitely. This one, perhaps a little harder to see, but nevertheless, you can continue the pattern indefinitely. Here I have two shapes. If I took either one of them alone, there is no way of tiling the plane with it. You always get a gap somewhere, like here or like here. But if I use them both together, then I can, with this kind of configuration, cover the entire plane. Here I have another one, a little bit harder to see perhaps, that it does tile the plane, but indeed it does. And here I have an arrangement starting it off, and this pattern will continue indefinitely. Alright, there's some examples. Now, here I have a pair of sets of polyominoes. Each of these SP and SQ is supposed to be a finite set of polyominoes. And you're supposed to have some listing of these things. I've just done this fairly randomly, but the idea is that you have some computational way of listing all the polyominoes sets one after the other, and I've imagined doing it here. Now, the universe then that I'm talking about consists of two such sets, two distinct finite sets of polyominoes. And the dynamics of this universe is, well, you start with two of these. Well, that's not much because this is the empty polyomino set. There aren't any in there. But the rule is that if you have a pair of polyomino sets, you look at the first one and see whether that will tile the plane. If it will, then you move on to the next one. Leave the other one alone. So if you have SP, SQ, if SP will tile the plane, you go on to SP plus 1, SQ. But if SP does not tile the plane, well, you still go on to SP plus 1, but then you swap the two over. Well, it's a simple little rule, pretty stupid universe, but the point I want to make, well, 2 points. First of all, it's a completely fixed rule as to what it does. It's even a deterministic universe. What it does at the next stage is completely fixed by what it was at the state before. Secondly, it's a non-computable universe. There is no computer simulation of this universe. So here we have the evolution will be something like that. The evolution is deterministic, but it's non-computable. Now, why do I say it's non-computable? Well, I can't tell you why, I'm afraid. It's a theorem due to Robert Berger, which I have employed to make this statement. This is a mathematical result which follows from Robert Berger's theorem. Robert Berger's theorem tells you that if you're given a set of polyominoes, and if you say has some computer program which is supposed to decide yes or no whether that polyomino set will tile the plane, well, it'll fail sometimes. What Robert Berger's theorem tells you is there's no computer program which will, for every set, say yes or no whether it will tile the plane. And it depends upon the existence of tile sets like the one here, these particular 3 tiles, that's an example, which will tile the plane, but they tile the plane in such a way that the pattern never repeats itself. I think I might leave that one up for a while so you can stare at it and see if you can see how it continues. Well, it's not the kind of thing, it'd probably spoil the rest of my lecture if you spend the rest of the time looking at that. But I can guarantee you that there is a way of continuing that to cover the entire plane, but it never repeats itself. And Robert Berger's theorem depends on the existence of things like that. It's not just that, but it depends on the existence of tile sets of that nature. But what this tells you then is that even if the universe is deterministic, which it may or may not be, it needn't necessarily be computationally deterministic. That is to say, there need not be any computer simulation of that universe. And this particular universe, even though it's quite a simple thing, has no computer simulation. It's a non-computable universe. So what I'm trying to say is in the actual universe, there must be some ingredient a bit like that. Of course, not really like that, but a bit like it in the sense that it has something outside computation in it. Well, really, we have to ask the question, what is the actual universe like? And what do we know about the actual universe? Well, I talked about the large and the small and all that, but I really have to talk about the laws of physics. And the laws of physics, well, I've schematically put them all on this nice slide for you. Of course, I've left out some of the details, such as all the equations, but the point I want to emphasize is that laws of physics, as I said at the beginning, seem to fall into two classes. There are those laws of physics which describe large-scale objects or macroscopic objects. Those are classical laws. I've called this the classical level, and the laws of Newton, of Maxwell with regard to electric and magnetic fields and light and so on, and Einstein when you have to consider large velocities or large gravitational fields. These have the property, I'm using the letter C for all these things, these have the property that they're deterministic and computable. Well, I've got a bit of a question mark at the end there. The reason for that question mark is that the laws of physics as we understand them operate with the continuum, they operate with continuous parameters, not with discrete quantities. And the notion of computability that I've been talking about up to this point refers really to discrete things. So there's a bit of a problem here which I'm not really trying to address. The reason I've drawn this question mark with it sort of dotted is that I want to consider it as something which maybe we don't have to worry about. So I'm trying to argue, okay, there might be a problem there, but let's forget about it. That's not the real point I want to get at. I think it's unlikely to be the main issue here. I've also put time symmetry, but forget about that. That's for another talk, really. Okay, that's the large-scale things. What about the small scale? Atoms, molecules, fundamental particles. For that, we need the theory of quantum mechanics. Now, quantum mechanics, although you probably think quantum mechanics, oh, that's also fuzzy and indeterministic and so on. But if you stay down at the quantum level, there is this equation known as the Schrodinger Equation, or the Heisenberg equation, which is basically equivalent to it, which tells you how your quantum system evolves with time. And the point about this is that it's also deterministic and computable. You may see a little faint arrow at the end of there. It's actually considerably fainter than this arrow because the Schrodinger equation is what's called linear, which means it doesn't have a lot of the complicated behavior that classical systems have. And it's, if you like, rather more clearly a computable system, even than classical physics. Now, if that were all that there was to quantum level physics, you would not really have the whole story, because what you really need is something which is called what's called making a measurement. That means that you have some quantum event which gets magnified until it basically comes down here. So you have something which comes down from this level to this level. Sort of familiar example is the Geiger counter. You can have a particle entering your Geiger counter and it makes a click. So that the particle is a quantum object, and when it makes a click, that's a classical level thing. So that the measurement process is coming in there, and according to quantum theory, that's where all the probabilities come in. The probabilities don't come in here. A quantum level system evolves in a completely deterministic way. It's only when you do this process of magnifying to the classical level that you get the probabilities and the randomness. And that's the way physics is done. It's a funny kind of mixture between two completely different procedures. Nevertheless, that's the way we do quantum theory. And I mentioned at the beginning that I had qualms about quantum theory. Well, that's what it has to do with. So I'll put that there. Now, I have to say, I think, a little bit more about quantum theory, because I can't assume we all know, we're not all experts on quantum theory, I suppose. So I'll have to give you a quick 2-minute lecture series on quantum mechanics. So I'll do this by describing this sort of archetypal quantum mechanical experiment, which is the Two-Slit Experiment. And I'm imagining we have some kind of quantum particle, let's imagine they're photons over here, being emitted by a source. That sort of lamp thing is meant to be a source of photons. Let's imagine that they go along one at a time. They go through a couple of slits here to a screen behind. And when they reach the screen, it makes a spot, and that spot is a macroscopic object. But between here and here, the photon is a quantum level object. Now, I want to describe the sort of basic puzzle of quantum theory. Let's imagine that I close off the bottom slit, just have the top one open, then you may find that a photon can get from the lamp to the through the top slit and reach a particular point on the screen. Now let's close the top slit and open the bottom one. I may still find that the photon can go now through the bottom slit and reach the same point on the screen. Now if I've chosen this point carefully though, and I now open both slits, I may find that the two things that the photon might do mysteriously cancel each other out, and suddenly it can't reach that point at all. So this is one of the basic puzzle, if you like, of quantum mechanics, is that alternative things which might happen sometimes can cancel each other out. Well, that's not the sort of thing you can have in ordinary classical physics, but the way one understands that is to think of between here and here, the state of the photon involves some mysterious kind of superposition of one thing and the other. We say alternative A is going through the top slit and reaching that point, alternative B is going through the bottom slit and reaching that point, and somehow these two alternatives coexist. That's the way quantum mechanics describes what happens. What's more mysterious is that the sort of coefficients, saying how much of each, are complex numbers. If these were simply ordinary positive real numbers, you might say these are the probability it does this and the probability it does that. But if they were just probabilities, you never get this kind of cancellation that takes place. The cancellation takes place because these are complex numbers. Well, those are numbers involving the square root of -1. You can plot them on a plane if you like. And when I talk about U, that's called unitary evolution, that's the thing at the top of that picture there. That's what's going on, preserving these superpositions. The Schrodinger equation is what's called linear. That means that if whatever A might do and whatever B might do, if you have a superposition of the two of them, it does the superposition of what A might do and what B might do. So Schrodinger's equation has that property, that in a sense, if you like, A and B simply go on merrily without even knowing the other one was there. However, once you make a measurement, you do something completely different. And that's the process R. It's called reduction of the state vector or a collapse of the wave function. That's going from one level to the other. And in that process, you simply do a completely different thing. You now take these complex numbers, see how far they are from the origin in this plot here, take the square of that, it's called the squared modulus, and the ratio of these two squared moduli give you the ratio of the probabilities of the two alternatives. Now that's a completely different procedure from this, but nevertheless that's what you do in quantum mechanics. And the fact that you have these two quite different procedures is one of the reasons why I have trouble thinking that this is a kind of absolute scheme which is going to last forever. Anyway, that's basic quantum mechanics for you. I want to tell you two of the puzzling features of quantum mechanics. One of them is something which is puzzling, but it's definitely true of the world. It's what's called quantum non-locality or quantum entanglement. These are experiments. The original idea came from Einstein and colleagues, and famous theorem due to John Bell showed that there was a real conflict between quantum mechanics and what you might expect. But what he really showed was the following, and I'll just illustrate it with an actual experiment that was done by Aspect in Paris a few years ago. You have a source in the middle here, photons going off in opposite directions, and detectors at the two sides which make measurements of the polarization of the photons. There's a choice which is made somewhere out here or out here. When the photons are in free flight, this is which direction you measure their polarization in. And what John Bell says is that the results of these measurements, if you like, the probabilities, the correlations between what happens here and here, cannot be explained in terms of these two photons being separate, independent objects. In some sense, they're still connected to each other right up until the time they're measured. So that's what they mean. They're entangled. The state of the pair of photons is what's called entangled. The photons are still, in a sense, one thing until they're measured. So it's a really remarkable fact. And it's a fact. It's something which has been experimentally determined. Now I want to tell you something else that's very puzzling about quantum mechanics. So puzzling that I don't believe it. Well, not only don't I believe it, but Schrodinger didn't believe it either. It's Schrodinger's famous cat. In fact, he suggested this thought experiment, and I emphasize it's a thought experiment because Schrodinger would never have allowed this experiment to be performed on actual cat, I'm sure. The idea, and I've got a sort of slightly different version of it here, the idea is that you have a quantum experiment, and I've here got a photon, which impinges upon this here half-silvered mirror. What a half-silvered mirror does is to take each photon and split its state into two. So that part of the photon, if you like, goes this way, the other part goes this way. The photon is in a superposition of going this way and this way. This part of the photon state encounters a detector which fires a gun and kills the poor cat. The other part of the photon's state goes away and the cat lives happily. Of course, if the whole thing is to be treated according to the rules of U quantum mechanics, if you treat it at the quantum level, what you would get is a cat also in a superposition of being alive and dead. And Schrodinger put forward this suggestion just to show how ridiculous his own equation was when applied to a cat. And he was saying, don't believe my equation when it's applied to cats, more or less. Now I think nowadays people are much more inclined to believe Schrodinger's equation than they are to believe Schrodinger. So they tend to say, well, somehow we've got to understand the cat is in a superposition of being alive and dead, because that's what Schrodinger's equation says. And we have to come to terms with it in some way. Well, I won't go into all the contortions that you have to go through to make sense of this. All I'm going to do is impose my own viewpoint on you, because I haven't time to describe the others. Anyway, it's sort of more convenient for me to do it this way. Which is that the conventional approach is only an approximation to something which we don't yet have. We don't yet have the correct theory which tells us what to do, which will be some kind of union between all these schemes, which involves a change in the very rules of quantum mechanics. And this new procedure I'm calling OR. OR stands for Objective Reduction, but it's a nice acronym, of course, because it also stands for OR, which tells you that the cat is dead or alive. So you can remember that, I think. Okay, well, what form does this idea take? I want to give you, I mean, a cat is sort of raising all sorts of additional complications, such as is the cat conscious and things like that. Let's not worry about that. So I can replace the cat by a lump of material, and it's a simple experiment now, but if the photon goes one way, it moves the lump from one place to another. If it goes the other way, it leaves the lump alone. And the question is, does this superposition persist, or does it somehow only persist for a very, very short period of time and become one or the other? So my argument is that the superposition of the two lump positions becomes either one or the other in a certain time scale. It's like say, a uranium nucleus which might decay into one thing or another thing after a certain lifetime. And what I'm saying is that you can calculate that lifetime by working out a certain energy. It's very similar to a uranium nucleus, where there is an uncertainty in its actual energy. The reciprocal of that energy uncertainty, is a measure of the lifetime of the state. And so I'm saying there's something similar here. There is a basic uncertainty in the energy of this superposition, which you can compute by considering the following. What you do is you consider that the lump is in one position, and then you try to pull it away, imagining that you're pulling the lump away from the gravitational field of where it was before. So it's like imagining that there were two instances of the lump superimposed. You pull one away from the other, only considering the gravitational effect. How much energy does that cost you? And that's this energy uncertainty. And then the time scale I'm talking about is, well, that's Planck's constant essentially, divided by this energy. This is rather similar to certain ideas put forward by other people, Karohazi, Diosi, and some others who have tried these suggestions of this nature. I think I'll put that up on the other side here for the moment, just so you can see what the formula is. The reasons that I have for believing something like that have to do with what happens when you consider general relativity. You see the lump positions will each distort space-time in some way, And here I have a kind of schematic picture. Here the lumps are together, the two instances together, and then one gets displaced away, moving sort of a ripple in the space-time as it goes, and now you have a superposition of two slightly different space-times. And the fact that these two space-times are slightly different means that you have a kind of uncomfortable state. There's a basic conflict between the principles of Einstein's general relativity and the principles of quantum mechanics. And this conflict is something which shows up in these situations. Now I'm trying to find my original picture of all the scales, which I probably put somewhere that I won't be able to find it. You will probably remember at the bottom of that transparency I had things called the Planck Length and the Planck Time. And usually these are things that people worry about when they start to combine quantum mechanics with general relativity. And because they're so far off the scale, they say, well, they can't have any relevance to anything. But if you actually work these formulae out, you find that that's not true at all in the way I've described it. Let me just illustrate the kind of way in which these numbers come in. So here we have again the superposition I'm regarding as something unstable. It decays into one or the other. Now, suppose that this lump here were a nucleon. Let's just say a proton or a nucleus. Well, let's say a proton. And you had it superposed in two positions. How long would it take to jump to one or the other? Well, if you imagine that that particle is a hard sphere of a radius of the sort of radius people tend to consider, which is what's called a Fermi, then it would take a few million years. Which is just as well, because there are experiments which have been performed by people, in particular Anton Zeilinger had a very impressive experiment on neutron interferometry, showing that neutrons do exist in superpositions like this, and they don't go to one or the other, but they only, in his experiment, would be a tiny fraction of a second that they would be held in this superposition, certainly not a few million years. So that's just as well that this time scale is very long. It means that there is not conflict between this proposal and experiments that have been performed on neutron interferometry. In fact, this is if you don't take the idealization of a hard sphere, the time scale is far longer. But so let's not go into that though. More appropriate though is if you consider something like a water speck, a little tiny droplet of water, then you can get some feeling for these time scales. If it was something like 10 to the minus 5 centimeters in radius, then the time would be a few hours that it would go to one or the other. So it would be a quantum system for quite a while. If it were a micron, it would take something like a 20th of a second. If it were 10 to the minus 3, a thousandth of a centimeter, it would take something like a millionth of a second. So you see, this is sort of more quantum mechanical on this side, it's more classical on that side. And that tells you, sort of roughly speaking, the turnover between one or the other. Now I want to make an important point here, and that is, if you wanted to try and detect whether this effect is correct or not by experiment, you have to be very careful to isolate the system from its environment. A non-isolated system, well, because of this entanglement thing I was talking about, the system is entangled with all the particles in the environment. And the likelihood is that the particles in the environment are going to move more, going to cause more mass movement than the thing itself. So the thing will probably reduce much more quickly. What's more, the process will be completely random because the environment is random, and so we would have no way of distinguishing my proposal from the conventional one. So the thing is, unless you can have a very well isolated system, you're not going to be able to see any new effects that might be present owing to this. In fact, there's a good chance that experiments, I was talking to Zeilinger in his group quite recently, and it looks that it's quite plausible that an experiment can be done to see where this effect is true. So I'm putting my neck on the block here. It's something which may well, in the next several years, be tested, so we'll see if it's right or not. But the more important question for the purpose of my talk is, how on earth does this have any relevance to the human mind? After all, the large and the small, what have I said about the human mind here? This is the large and the small. The human mind is supposed to have something to do with this process here, which is where the new physics comes in. So what I'm trying to say is there has to be something non-computable about this process. You might say, why do I argue that it's non-computable? Well, there are some reasons coming from quantum gravity to suspect that there may be something non-computable in this process. But the reasons are not terribly watertight. The other reason really is just, well, we don't see it here, we don't see it here, we don't see it in this randomness. Where can it be? Well, it's got to be here. Well, you might say it's a pretty weak argument. I don't altogether deny that. It's the Sherlock Holmes argument, which says once you've eliminated the impossible, whatever remains, no matter how improbable, must be the truth. And so that's what I'm saying here. Well, whatever you might say about the strength of that argument, it seems to me that that has to be, if you follow the rest of what I'm saying, it's pretty hard to see where else it could be. I'm not saying it has to be there, but it's hard to see where else it could be. But there's still a problem, even if you believe that, and that is, how on earth can the action of the brain be dependent on this process? I said you need this very good isolation. It has to be so good that so far no experiment in physics has detected this effect, even though it's just about within the scope of present-day technology. So what about brains? Well, here I have a little piece of one, rather poorly drawn, never mind. I've drawn a couple of neurons, and of course there are lots more neurons in the brain than just these two, but the point I want to make is that if it were just a matter of neuron action, we wouldn't have much scope for this, because neurons really do disturb the environment. I mean, the signal which goes along a neuron, along the axon, will disturb the environment, and so the OR process will be just like the standard random one, and we're not going to get anything out of our quantum mechanical ideas here. So you have to look more deeply at what's going on. And one of the essential ingredients, of course, in the action of the brain is what happens at a synapse. A synapse is where the signal goes along from one neuron down part of the axon here and triggers off a signal on another one. In fact, you have to collect together impulses from various places, and some of them add, some subtract, and the question is whether this will cause the next neuron to fire. If you knew how all these connections behaved, how strong they were, if you like, whether they're positive or negative, you could then, in principle, simulate the action of this brain on a computer. It's very like a computer, in fact. So I would have to argue that there is something in what controls the strength of these synapses which is not computational, which takes advantage of this missing physics. And in order for this to have a chance of working, you really have to look more carefully into what's going on in neurons. Neurons, after all, are not simply wires and transistors. They are very sophisticated cells. Cells behave in very complicated ways, and they are very, very elaborate, sophisticated systems. One of the ways in which they achieve this sophistication is through a substructure of cells known as the cytoskeleton. I only learned about these things between writing the Emperor's New Mind and Shadows of the Mind, so you don't see any of it in the Emperor's New Mind, but they feature quite strongly in Shadows. I learned about the cytoskeleton from Stuart Hameroff, and in particular, he told me about these little tubes known as microtubules. They certainly inhabit neurons, axons, dendrites. They're all over the place. They inhabit other cells as well, so one has to look for some role that they have in neurons distinct from the role that they have in other cells. And there are certainly many differences one can pinpoint. I don't want to go into that particularly here, but let me tell you something about microtubules. There are two reasons that I found microtubules to be rather promising in this respect. One is something that Stuart Hameroff himself was very concerned with, a very interesting idea. As far as I'm aware, it's not, it's only kind of a suggestion which has some kind of confirmation of a general nature, but not of a very specific nature, namely that microtubules are capable of doing some kind of signaling themselves. His argument was that these little tubulins, the tubulin is the protein out of which the microtubule is built. It's a little peanut-shaped protein consisting of two pieces called an alpha and a beta tubulin. together they form a tubulin protein, and the microtubule is made up out of a very sort of systematic array of these tubulin proteins. Now the tubulin protein can indulge in changes of state, what are called conformations, and they seem to have at least two different conformational states. A slightly different shift in their shapes, if you like. And according to Hameroff, this is to do with the placement of an electron centrally in this tubulin. Well, whatever it is, the argument is that if the tubulin is one state or the other, it will influence its neighbors to be in one state or the other in a certain way that you can calculate, and that this will send signals down the microtubule, make the microtubule act like what's called a cellular automaton, a sort of little mini computer. So the idea was that, okay, maybe the brain is still a computer, but it's a computer with a great deal more computer power than one had any reason to believe before one could take these microtubules into consideration. That's not good enough for me, because I need something non-computational, something where the OR process really comes in a serious way. So what this means is that if these Hameroff processes are taking place, one has to consider that they might take place as quantum superpositions. So this is what's called the action of a quantum computer, that you have these cellular automata-like activities, but acting in superposition, and that you have to consider that it's really a quantum process. Now that would be all right, provided you have very great isolation from the environment. And so there's a big problem. How do you manage to get these microtubules very, very well isolated from their surrounding? Well, there are some suggestions as to how that takes place. I don't want to go into that here, but that, of course, I appreciate is one of the major problems you would have to overcome in any model of this nature. Now, the idea here is that not only do you get these superpositions, but you need something where when enough of these microtubules are acting together in concert, and it would have to be many, many neurons, all with their microtubules all acting together, there will be enough movement in the microtubules that this process that I've been talking about here starts to operate. It's in the movement of the tubular proteins. And you can actually calculate how many neurons should be involved for a state reduction process, using the kind of scheme I've been talking about here, to take place in the order of about a half a second. Why do I say that? That's because there are various experiments performed which suggest that a conscious action or conscious event takes something like a half a second. So that if it's related to this OR process, it would be a state reduction of the order of about half a second. And you can then calculate how much mass movement would be involved in that, and if it's in these protein molecules here, therefore how many neurons would be involved. There are some uncertainties in this, but it comes out to something like 10,000 to 100,000 neurons, which rather strikingly is the sort of number that people say, for quite other reasons, are likely to be the number of neurons involved in a conscious perception or a conscious event. So at least there's scope for some kind of tie-in between these ideas. There are all sorts of questions, though, that one has to raise here. For example, how do the microtubules influence the synapses? Well, I've drawn here one suggestion. There are a number of different ways they might do it, but one suggestion here is that the synapses are often of the form of what are called dendritic spines here. This is the dendrite here, and here's the axon, and there are these things called dendritic spines, which can be influenced directly by microtubules via another part of the cytoskeleton known as actin, and this could change the strength of the synapse. And so the idea would be that you have a conscious event takes place when a state reduction takes place and many, many microtubules all together, and the altogether influence in concert a whole lot of strengths of different synapses. And therefore, even if you think of the brain as a computer at any one moment, it's a computer which is changing all the time under the control of some deeper process where this OR ideas coming in. So that's the rough scheme. There are lots of problems, such as how do you get the quantum state across from one to the other, and so on. I'm rather intrigued by these molecules which exist in synapses known as clathrins. The sort of reason being that, rather like microtubules, they have a high symmetry, and structures with high symmetry are the kinds of things which are conducive to large-scale quantum processes. This is a sort of scheme of I don't know if you can make sense of that picture, but it's the sort of scheme that we are putting forward as a suggestion for what's involved in consciousness, that you have this quantum coherent activity, first of all taking place within the tubes, shielded from the outside by the microtubules themselves, something like a superconductor or superfluid, which goes right across many, many objects. The superconductor is something that you have to describe in a kind of holistic way. You can't say that it's a feature of the individual units. The state applies to the system as a whole, and it's something very similar one would need here. The brain, after all, consciousness seems to be a phenomenon which applies to the brain as a whole, and it seems rather tempting to think that it's something like a quantum coherent state. Superconductors are things which originally were believed to exist only at temperatures almost at absolute zero. However, in recent years, it's been discovered that you can have superconductors, what are called high-temperature superconductors, which are about halfway to what one needs here. They're not body temperature yet, but they're about halfway there. And there seems to be no obvious reason why high-temperature superconductors shouldn't exist at something like body temperature. So that would be required in this process here. You need some kind of pervasive quantum state going right over large areas of the brain, and now and again they start to involve the microtubular proteins. These then start getting involved in the computation, superpositions of these things. They reduce the state to one thing or another. That's where the OR comes in. That's a non-computational process, according to the scheme, that influences the way the synapses behave, and so it changes the way the brain acts. And so, according to the scheme, that is what's involved in consciousness. Of course, there's a great deal of speculation in these ideas. I don't deny that. On the other hand, there are ideas which are, in principle, subject to experiment. I mentioned the physical experiment that I hope will be done before too long. There are also many other ways that one can get hold of this idea from biological end of things and so on. So I think that it is something that maybe it'll get shot down in a few years, but at least that makes it science. So I'll put this back up here. It's some attempt at what's going on here. In order to argue for what can be going on here, one needs to know something about this and this as well. So I would argue that really finally to know what on earth is involved in mentality, I'm not saying even this model, if everything works here, it still doesn't explain why consciousness is there. We need something deeper than that. But in order to have an understanding of that, I do believe that we're going to have to really appreciate this whole scheme. It's not just trying to look at one little bit of it. We'll have to bring everything together. Thank you very much. I'm happy to take questions. I'm not quite sure how this is being organized. Should I do it from here, or what do you want to do? Right. I can't see people very well from here. Yes. Okay.
Go ahead.
Up there, yes. Go ahead.
Thank you for coming, Dr. Penrose. My question is a little bit of consciousness, but mainly it covers the very large and very small.
Right.
It has to do with a thing I've wondered about for a while, is what is the speed of gravity? There's obviously the perception of it, but then there's the interaction.
Right. So the question is, what is the speed of gravity? Well, I guess there are two answers to that question. Gravity is very like light, and ripples in space, these are things known as gravitational waves, or sometimes called gravity waves, which are believed to exist, well, we now have good evidence that they do exist, in systems, large systems where you have bodies rotating around each other, and they will send these waves off, and these waves travel with the speed of light. So the speed of gravitational influence, in that sense, is the same as the speed of light. Another way of putting that is that a graviton is a massless particle, and massless particles travel with the speed of light. However, that does presuppose that we know how to combine gravity and quantum mechanics. So talking about gravitons is perhaps not appropriate quite at this stage of our understanding. But it's certainly true that an influence, that is to say, if you wiggle something here, then that will be felt a long way away. The gravitational influence, or the change in the gravitational field, if you like, will be felt a long way away that in the time that it would take light to go that distance. So it's the speed of light. On the other hand, there are effects which can't really be quite thought of that way. I don't know if your question has to do with that. Depends if you're going to... Sometimes people worry, for example, about black holes, because a black hole, you see, is supposed to be a region where light can't get out, and so how does the influence of that black hole escape? But the thing is that, sure, gravitational influences travel with the speed of light, but in the formation of a black hole, you have a gravitational field which, as the body collapses, that field is there, and it sort of gets stuck. And it's only changes in that field which would travel with the speed of light. So the field remains, and any change in that field would travel with the speed of light. So if anything changed in the object after it fell into the black hole, that object, the change in that couldn't escape, so you'd never see it. But the field of the black hole itself, you would still feel outside. I'm not sure whether you were addressing that issue, but I thought maybe it was relevant to your question.
Thank you.
I can't see anybody, so you have to tell me.
Yeah.
You do it, yes.
Last year, Daniel Dennett was in this lecture series. He said that he spoke to you about your ideas of consciousness and computation, and he had some troubles with your ideas. I was wondering if you could describe where he differs with you.
Well, he certainly has a different view. Well, he's very much a computationalist. He seems to take the view that, in fact, he almost takes the view that consciousness isn't a real phenomenon at all, but it's a sort of illusion. He's rather extreme in this. I mean, there are various different gradations of viewpoint. He certainly is a computationalist in that he would say that whatever it is that we describe using the term consciousness, it's a feature of computation. And basically, it's because that's all he considers that we need to know about. One of the things it's a bit difficult for me to argue this because I'm not quite sure what he would say. I've told him many times about the types of arguments that I've used, and I haven't heard him refute them exactly. He tends to take a different position. But one thing he does tend to say is that I don't accept natural selection because I don't believe that consciousness is computational. I would want to argue quite strongly that I'm perfectly accepting of natural selection as a process which takes place and which has governed how our consciousness evolved. But I would argue strongly, I think what he's saying when he says I don't believe in natural selection is that I don't accept that natural selection is all you need to explain the phenomena of life and so on. I think it's absolutely crucial that natural selection is taken in the context of whatever physics is going on. So if you had a different physical world, you might still have natural selection processes, but they would evolve quite different things. It depends on the details of the physics. And what I'm saying is that the details of this physics include something which is outside computation. And that in order for consciousness to evolve, it has to take advantage of that. But it's still the process of natural selection which is operating there. Where I differ with Dennett, I think, is that I argue that it does crucially depend on the way that the physical world operates, and in particular, it depends upon some non-computational process in the way the physical world operates. He doesn't seem to consider that it's necessary to go into these issues in his discussion. I may be misrepresenting him. I still don't understand why the arguments that I presented at the beginning of this talk don't seem to worry him. Maybe somebody else could. And it seems to me they are pretty clear arguments that there is something not included in computation involved in our understanding. But my impression is he doesn't fully understand those arguments, but no doubt he'll have some different argument. Yeah, I'm not sure where you're pointing. Over here, yes.
Dr. Penrose, if I could just pick up on where you trailed off there.
Sure. Yes.
You're saying that there are propositions that people can understand are true that are non-computational, that a computer could not demonstrate.
No, it's not quite that.
No?
It's not any individual proposition. You have to be careful about this. What's non-computational is a family of propositions. And any one of them, okay, you can say it's a computational matter to say whether it's true or false. You just make a computer say, given that proposition, you say yes. And that's a computational procedure. So for any individual proposition, the question does not arise. The question only arises when you consider families of propositions. So, okay, now you can go on.
Okay, well, yeah. I was going to discuss the Lucas paradox, which, in this context, you could come up with a proposition which is Roger Penrose cannot consistently believe this sentence, which I'm sure you're well aware of. And that would seem to show that you can apply the same sort of reasoning to human beings that you can also apply to a computational system. So, how would you respond to that?
Well, I would regard that as irrelevant to what I was saying. It's certainly true that there is some kind of familiar relationship between the Gödel theorem and sentences of that nature. In fact, he was stimulated to produce his theorem by considerations of that nature. Of course, the Gödel theorem is not of that nature because it is a precise mathematical statement. Whereas things of that nature, you had a rather complicated statement. A simpler one is, this statement is false. And a statement of that nature is simply self-contradictory. And statements of that kind can be made in the English language. It's not really relevant to the discussion because I'm not talking about this form of the language and so on. I'm talking about mathematical propositions which are not dependent on any particular individual. They're statements of mathematics. That particular statement is one of these self-referential statements, which is not really relevant to my discussion.
Well, I think that it is, because Gödel's proposition was essentially, with reference to a particular formal system, this theorem is not provable, or this statement is not provable within this system.
Yes,
and he removed the explicit self-reference. But
you can't actually make it say that. It's a little bit of hard work. That's a rather glib way of saying what the Gödel statement says. It refers to families of statements, first of all. You can't actually make a single statement say that. It's a little more complicated than that. So it goes back to what I was saying, question of making families of statements. But the argument that I make is not the same as Lucas's argument. So, okay, you can argue against Lucas if you like, but the arguments that are made in Shadows of the Mind, I consider they actually go into these questions quite carefully, and that particular statement is not part of those arguments.
Okay.
So you can make it if you like, but it's not. It's a self-referential statement, and we know we can make self-contradictory statements which are self-referential. We can make all sorts of things like that. It's not. It was a guide to Gödel in his production of his theorem, but you can interpret the particular sentence that comes up in that kind of way if you like. But it certainly doesn't say it's false, and it doesn't say it's not assertable. It says it cannot be proved by means of rules which have been laid down specifically in the system. And it's a different kind of thing.
Okay.
Okay. Me? Right, wherever you are. Yes, these lights make it a little hard for me to see. Oh, right up there, is it? Yes. Me? Go ahead.
Oh, is that me? Okay. All right. Dr. Penrose?
Yes.
I have a question more about the large and small.
Yeah.
Earlier we were talking about the nature of gravity. how do you reconcile conceptually the idea that gravity is a particle or a wave with the idea that, according to relativity, that it's a curvature of space and time itself? I mean, in linking the quantum and classical worlds.
Well, of course you can have waves in the classical world. That's not necessarily a feature of quantum mechanics. I mean, electromagnetic waves are waves, and gravitational waves are waves. They're classical waves. There is a feature of quantum mechanics which says that given a wave process, there will always be an associated particle or a particle description. And these are it all has to do with the principle of superposition, if you like. A wave in quantum, if you take a single particle, then that particle could be here, or it could be here, or it could be here, or it could be here. And all those different positions of that particle have a different complex number attached to it. So we have, if you like, a function which describes the complex numbers for all the different positions of that particle. And that pattern of complex numbers is the wave, if you like, which is used in quantum mechanics. So if you like, the wave-particle relationship comes about via the principle of superposition. So that's really the mystery of quantum mechanics, is the superposition principle, not so much the fact that you have this kind of two ways of looking at things, either in terms of waves or particles, because really that's just saying either you think of this whole wave of different alternative positions that the particle might have, or you think of the individual positions. And it's just two different ways of thinking about the wave function or the state vector. I don't know if that answers your question. Gravity, you might say, you could apply the same principles as one tries in the case of electromagnetism, and people try to do this. There's a large body of activity, many, many people who try and what might be called quantize gravity. My own ideas are that this isn't quite right. It's partly right. But this is suggesting that you take the rules of quantum mechanics as they stand and apply them to Einstein's theory of general relativity. What I'm saying is, no, you're going to need to modify the rules of quantum mechanics as well. That the principles of general relativity and those of quantum mechanics are in a basic conflict. And to bring them together, you're going to have give on both sides, not just give on the side of general relativity. There's going to be give on both sides. I don't know if that answers your question, but
sort of.
It's some attempt at it. Yes, there's a question down here, is there? Yes.
Okay. First I want to make a short comment, and then I want to ask my question. They're related.
Mm-hmm.
I think I agree with you, for what it's worth, that comprehension or insight is not computational. I don't think your arguments establish that, but I think that that's probably still true. It seems to me, now I want to get to my real point, that that's what's essential about insight or about comprehension, or for that matter, even bare consciousness, say, of redness. That's what essential to those things is not whether they are or whether they are not computational. Now, it seems to me that if I understood you, I don't see how you get from there's stuff in quantum physics that is not computational in the sense that you've been using the term, and your claim, and I'll agree to it, that there's stuff in the very nature of consciousness which is not reducible to the computational.
Mm-hmm.
How do you get from that similarity to your suggestions about how we can account for or give an account of what consciousness and insight and all of those things are? I mean, even from even by bringing in the quantum stuff and the non-locality stuff, I don't see how beyond the similarity in that neither of them is computational in the sense that the phrase has been used, that your suggestions help me to understand what consciousness is or how consciousness arises, unless by how it arises you mean you only want to talk about some physical events, but you don't see any way of connecting the talk about the physical events to the internal, that is, as experienced by me, the internal characteristics of consciousness, insight, or comprehension.
Yeah, I think, let me address your question by saying, I don't consider that anything I've said here says a great deal about why we perceive what awareness is, or why redness is something we perceive as redness. I'm just fastening attention on understanding and the issue of computability because I consider that it gives us a route towards the kind of thing that we're going to need to know. I'm not saying that it in itself sheds much light on these questions, and I would agree with you there. I think that the mystery of perception of the color red and all sorts of other things is hardly touched upon by these considerations. But the trouble with that is, you see, you can worry about, why redness is red and so on. It's not going to get you anywhere with regard to trying to understand what kind of physical processes might be involved there, or to get any further.
It's the physical processes which Boghosh and Magali have as their outcome, or some kind of emergent thing that comes about when they come about. You're interested in looking for physical processes which are accompanied by insight or consciousness.
You're saying that no matter what kind of a physical description I will have, it will only be a physical description of something which goes along with it, and it doesn't really...
Well, yeah, I mean, it seems to me that consciousness and insight, there's an internal side and an external side to it, and you haven't said anything about the internal side.
Well, you see, I think it does, you see. I'm agreeing with it, it's a long way away from it, and the question is, you see, when we use our understanding to come to terms with something, we are using, and when a child appreciates what a natural number is, that is using something internal. And that manifests itself externally. That's what I'm trying to say. One of the problems that philosophers are always having is, okay, the internal world seems just to be separate from the external world. How are you ever going to explain anything about our internal world from just how things behave? And I think that's the issue you're bringing up. It's a real issue. But what I'm trying to say is that I don't think it's quite as gloomy as that. I think that there are things where the internal, what we do internally, does make a difference externally. So you can begin to see that in different internal states, if you like, different states of consciousness lead us to behave in different ways. That there is really an objective effect of our consciousness, that conscious things, if you like, behave in different ways from unconscious things. So I think that I'm concentrating on that, and if we can understand that difference between how conscious things behave and unconscious things behave, then that may ultimately give us some insights into what it is that consciousness is, if you like, why it's there at all. I'm not saying that we immediately get to grips with that problem. I think it's a very difficult problem, and I'm agreeing with you that what I've said doesn't come really, very close to understand why this thing is here. What I'm trying to say is that in our, if you like, I'm going the long way around. I'm trying to say that because of some kinds of ways we perceive, they relate to something up here, and that tells us something about how this area works. So by going this route, we're at least getting some insight into this. But I think it'll be a long time before we really get any appreciation, or if you like, why consciousness is there at all. What is it? I agree with you.
Are you suggesting that we'll go through, this may result in something like a conceptual shift of
it will eventually,
metaphysics?
Yes.
Thank you.
I think so.
Dr. Penrose, excuse me. I have a question on the tension between the perception of free will and determinism. With the existing structure of the deterministic quantum level U governed by the deterministic Schrodinger equations, and then the collapse of the wave function R, which is probabilistic, then it seemed that there could be a possible resolution to that tension, so that at some quantum level there was a random element in the brain which might propagate up through the chaotic structure, but basically algorithmic commutable structure, so that I choose taco salad rather than tuna fish sandwich for lunch.
Yes.
But with your proposed OR theory, it sounds, is that deterministic, though non-computable, so that in fact there is no probabilistic element which could account for free will, so that our consciousness is actually deterministic, although it may be a moot point since it is non-computable. So it is determined what I will have for lunch next Tuesday, though in principle we could not calculate it. So is your OR theory deterministic?
Well, it's certainly a relevant question. I haven't actually committed myself on that one. The toy model I gave was an example which was deliberately deterministic, just to make quite clear that the issue of determinism is different from the issue of computability. However, when it comes to this actual process here that I consider is present in the physical laws, or we don't know what it is yet, I don't really have a claim to make about that. It might contain a non-deterministic element, but it's not simply random. Of course, in the early days of quantum mechanics, many people did try and relate this to free will. And they tried to say, well, now we have a universe which is not deterministic, there is the home of free will down there. But then people realized, well, it's not much of a free will if it's purely governed by random processes. Somehow it's already random anyway. So some other people suggested, well, maybe it's not quite random and something comes in and influences the probabilities, something from outside or something like that. And then you might argue that's not altogether scientific. Well, my own position on this is not really... I think the issue of free will is way beyond anything I've said here. But let me make a comment or two about it. I think it's conceivable that the scheme that's here would actually be deterministic. But it's not going to be anything as simple as the kind of model that I did show you there. That model is a sort of first level of non-computability. In fact, it's true that you could do the whole argument all over again with what Turing calls an oracle machine. Turing actually went into all these things very carefully. He had a very sophisticated paper where he considered not just computability, but different levels of non-computability. And he really discussed this in great detail. Now the thing is, you could consider at each stage of these levels of non-computability the same argument that I gave, or a different version of it. There's a Devil Theorem will apply at each level. And so it tells you, if you believe my arguments, that there must be something in our consciousness which uses something which transcends all those levels of non-computability. So the procedure here has to be not just straightforward non-computable in the sense that that toy model was, but something which is very, very sophisticatedly non-computable, and really is at the borderline of whether it's deterministic or not. So I think until we really have a better handle on that, it's hard really to address your question. But I think there is a deep question there, and I'm not one of these people who dismisses the idea of free will as somehow meaningless. I think there's a real question there, and that this question is a deep one. Even all the time, even sort of in legal issues, people take the view, is somebody responsible for their action or not? And then the question is beginning to come up, could you say a computer is responsible for its action, and so on? Well, does a computer, in my mind, it has to be aware, it has to have some kind of consciousness if it's going to have any kind of responsibilities or rights and all that sort of thing. And I don't believe that the present day idea of a computer-controlled robot would have any of these qualities, simply because it doesn't, well, my arguments would be that it doesn't possess awareness. So we'd have to look to some other device which takes advantage of these processes that I'm saying here, and we're not anywhere close to that at the moment.
Thank you.